Hi, and welcome to Unit 7, Day 2, Electrochemistry. For this lesson, we're going to explore question number 2, which is thinking about the driving forces behind these electrochemical reactions. Like, what are they? Before we begin, just a quick review. We have already discussed these key terms for electrochemistry. Take a moment to read through them and see how familiar you are with these key terms. If there's any key term that you're not familiar with, you may want to go back to your textbook to either look this up in the glossary or use the index to find these words so you can refamiliarize yourself with what they mean. All right. In addition to these key terms, in the very first lesson, we looked at what's called an electrochemical cell. This is an example of a voltaic cell. And in these electrochemical cells, we talked about the anode and the cathode. And the anode is where the oxidation reaction takes place, and the cathode is where the reduction reaction takes place. And that's what we see here. For this lesson, what we're going to be looking at, well, how do you know, before you even set up this electrochemical cell, that the zinc would get oxidized and the copper would get reduced? How do you know that? So in order to answer that question, what we use is we use a tool which is called the standard reduction potentials chart. And basically what it is it lists a bunch of half reactions. You can see all these half reactions here. And for each half reaction, it gives you the potential for that half reaction to undergo reduction. So if you look here, we have lithium with adding to 1 electron goes to neutral lithium. Well, what is the potential for that to happen? And the values that are written here, the potentials, the greater the potentials are, the more likely that reaction is to happen. And so if you have two half reactions, the one that has a higher reduction potential, meaning a more positive value, well, that's going to be the one that gets reduced because it really wants to do it. Because remember, the more positive or the bigger this number is, the more that reaction wants to get reduced. On the flip side, the smaller the number is, like if you look at towards the top here in this table, it's less likely to happen. It doesn't want to get reduced that much. So if you take something like lithium, and you can even think about your understanding from the periodic table, lithium is in group 1, and in order to have a full shell, it would much rather prefer to lose an electron than to do the reverse reaction, which is to gain an electron. All right? And so that's sort of what these things measure, the potential or the desire of a species to undergo reduction. This is not the table from your textbook. I think in your textbook, it kind of does it the opposite, where instead of having the more negative values at the top, it's the more positive values. So in any case, when you get a reduction potential chart, make sure you carefully read to see what the trends are in terms of the reduction potentials. So as I said, this is the tool that we use to figure out what gets oxidized or reduced. The more positive the reduction potential, the more likely it is to get reduced. There's a couple of terms that we use in describing things that like to get reduced or like to get oxidized. And these are the terms here: reducing agent, reductant, or reducer. We use those terms for things that like to become oxidized. Let's figure out what that means. So if you want to lose electrons, you want to become oxidized. And in order to become oxidized, you have to reduce something. So you are the agent to reduce that other thing. And so that's why if you want to be oxidized, you're called the reducing agent. And as we know, if you want to be oxidized, then your reduction potentials, these values here, are going to be more negative, towards the more negative. On the flip side, if you want to gain electrons, that means you want to be reduced. Well, in order for you to be reduced, you have to oxidize something. And so you're called an oxidizing agent or an oxidizer, an oxidant, because you will oxidize that other thing. And again, as we know in this case, then your reduction potentials are going to be greater because your potential for you being reduced is greater. So your E reduction potential should be more positive. All right, let's do a quick CFU to see if we understand what these terms mean: reducing agent, reductant, reducer. Remember, reducing agents will get oxidized, and oxidizing agents get reduced. So they kind of do the opposite. You may need to use either flashcards or find some way of memorizing that. All right, so in our CFU, we have several metals here: aluminum, silver, sodium, and zinc. You're asked to find what's the strongest oxidizing agent and which is the strongest reducing agent. For this, you're going to need the table in your textbook, which is on page 841. Pause this video to turn to that page in your textbook and see if you can find the answer. Okay, so here is the answer. These are the values from your textbook. So starting with silver, that is our strongest oxidizing agent. Why? Because of its reduction potential. It's the most positive one, or the biggest greatest reduction potential, and so that means it wants to get reduced. That means it's the strongest oxidizing agent. And the strongest reducing agent would be sodium, because it has the lowest, or the most negative reduction potential. And so, oops, sorry about that. And so therefore it's going to want to, it's not going to want to be reduced. It's going to want to get oxidized, making it the strongest oxidizing agent, reducing agent, I'm sorry. Okay, last thing is we're going to talk about quantifying the driving force of electrochemical reactions. So we kind of know what is the driving force behind electrochemical reaction. Whatever wants to be reduced will get reduced, and whatever doesn't will get oxidized. And so, well, how do we quantify that? We quantify that through these reduction potentials, or cell potentials, and it's a real simple equation. You take the value from the tables of the reaction that happens at the cathode, the thing that's being reduced, and you subtract from that the value at the anode, which is the thing that's being oxidized. And you're going to see some examples in a moment. But before you do, I just want to point out some of these terms, like electromotive force, cell voltage, or cell potential. That's what this value measures. It tells you the difference between the cell potential of an anode and a cathode. And the reason why that's the driving force, again, if you think about a ball rolling down the hill, when there is a great difference there between the top of the hill and the bottom of the hill, that ball really is going to want to roll down. That process is really going to want to happen, and so that's that's what's driving it here. Now, one quick note: when you calculate the E cell, if the value that you get is positive, so it's greater than 0, then you know it's a spontaneous reaction. And that occurs in a voltaic or galvanic cell. If the value that you get is negative, so if this value is negative, then you know it's non-spontaneous. That occurs in an electrolytic cell. Last and final note that these values are all standard occurring under standard conditions, which means the solution is at 1 molar, gases are at 1 atmosphere, and the temperature is 298 K. All right, so the best thing to do is to just see a bunch of practice problems on calculating the cell potential. You're going to watch this video which shows you how to calculate voltage of a galvanic cell, and then there are some practice problems that you can do here. All right, lastly, we're going to end this video with, again, you want to do your reflection and your summary. And then after that, you have some textbook problems that are listed here and also in the spring break document. Folks, I hope you have a wonderful spring break and a quality day. See you later.